Hi, hello everyone. Well, in this video, I wanted to make an explanation or an introduction and overview into what is sensors, no? How can we use sensors to monitor electrical machines? And then I will talk a little bit about data analysis. But in particular, I want to focus on what are the steps that you need to take into account when collecting data with a sensor, okay? Because that is not a trivial task, okay? Sometimes we can buy the sensor and we can connect it directly, no? Like plug and play. Well, sometimes there are scenarios in which you need to first pre-process the data of the sensor in order to record that sensor data and later perform an analysis of that data. Okay. So, well, in the previous classes, we discussed a little bit about motors. No, we discussed what is an electric motor, and in particular, we focus on some examples related to DC and AC motors. Okay, and the question is, well, why do we need to use sensors in electrical motors or in these electrical machines? And well, we have like two main goals. Okay. One goal is oriented to the fact that we want to control, for example, the speed or the torque that the machine is providing to the system that we want to move. Okay. In that regard, we need to use speed sensors, in particular, that is called an encoder, or maybe we need to measure the torque that the motor is delivering to the load. Okay. And in order to do that, we need to use a load motor, okay, in order to measure how many torque the motor is providing to the system that we want to move. But there is another case in which we want to also detect potential faults in the motor. For example, we want to know if there is a short circuit in the electric motor, in the windings of the motor, and we need to measure the current, okay, because a short circuit can produce excessive current. Also, maybe the motor has some mechanical misalignment, or maybe the stator on the rotor of the motor has some failure that is producing insufficient torque. And sometimes we can also produce overheating in the machine. For example, maybe we are overloading or we are demanding too much power to the motor, and that is producing a lot of heat inside the machine. And if we produce many heat inside the machine, we can melt or produce melting in the insulation of the windings, or maybe you can produce the magnetization. The magnetization is a problem because if you're using permanent magnets in your electric motor, in order to produce the magnetic fields, the magnetization basically refers that when you increase the temperature of a magnet, its magnetic flux or its magnetic field will decrease. Okay. And that is a problem, no? Because the magnetic flux will start decreasing, and since the magnetic fields are are the ones that are producing the torque, you will start to lose the torque capability of your motor. Okay. So in this graph, what I am showing you is what are the common causes of failure, in these electrical machines. For example, you can have rotor failure, you can have bearing failure, and also you can have electrical failures, miscellaneous failures, for example, misalignment in the shifts of the motor. You can also have old age. The old age also can produce failures in the machine. Contaminants like water, dust, oil, or grease can also produce failures. But let's say that the most common cause of failures in this type of electrical machines are overloading. Okay, overloading typically causes the failure of a machine. Basically, that means that we are demanding too much power or too much torque to the machine, and that also produces or is basically related to the possible electrical or mechanical failures or that the machine can exhibit. So I told you, one of the causes, well, one of the effects of overloading is the overheating of the machine. For the case of the permanent magnet synchronous motors, there is a problem, no? Because In this design, you can have magnets in it. Well, you have magnets in the rotor, and if you increase the temperature inside the machine, no, of the inside the motor, you will start to reduce the magnetic flux of the magnets, and consequently, you will lose the torque capability of the machine. Okay. So there is a problem. Or if you're using an induction motor, well, you have windings in the rotor and also you have coils in the stator. And if you increase too much the temperature of the windings and the coils in the rotor, you can melt the insulation. Okay, so that is another concern that we need to take into account. So how can we monitor the state of the machine? Well, basically we use sensors. Okay, and remember that the sensor is basically a device that can detect or measure a physical quantity, okay? Basically, the sensor is an electronic device that responds to any physical stimulus, okay? And this physical stimulus can be a contact between two objects, or maybe some, if the sensor is based on noise, like an ultrasonic sensor, well, we are responding to the change in sound, or if you're using a temperature sensor, you're responding or you're producing an electrical signals based on the change of temperature. And here I listed some sensors. For example, the temperature sensor is widely used for electric motors, but also in industry. No, the temperature is a common variable that we want to measure. We also have gas sensors, humidity sensors, a potentiometer, and the potentiometer is basically a variable resistance. Okay, it's a resistance that we can change its value by using a screwdriver or moving certain screws in the device. Okay, and also potentiometers can be, for example, resistance that changes value depending on the light or depending on the infrared light that incides in it. Okay. And also we have encoders, and encoders is like the device that we can use to measure the rotational position or the rotational speed of electric motors. Okay. So let's talk about first about what are the common types of temperature sensors that we can encounter. Typically, we have two types of temperature sensors, but in principle, they work basically in the same way. They produce electrical signal, typically a voltage, and based on the changes in temperature. No, that is the basic principle of operation. No, we have a change in voltage that is related to a change in temperature. And well, the most common types of temperature sensors are the thermocouples and the thermistors. Okay, so let me move this slide. Okay, so the first device is the thermocouple. The thermocouple is basically a device in which we have two elements. We have chromal and aluminum. Okay, so we can form a junction, okay, between this chromal and this aluminum. No, these are two metallic objects, and we can form a junction. And when we apply heat into this junction, we can produce in the other side, okay, if we place some conductors like copper in the other side of the metals, voltage, okay? So the effect is the following. You have a junction of two metallic objects, and when you apply heat to that junction, or heat or temperature to that junction, you will produce a voltage in the other side, okay? And that is related to the Seebeck effect, okay? The Seebeck effect basically states that um, when you, well, this is a little bit better illustrated in this animation. Basically, you are applying heat to your junction of your two materials or your two metallic objects, and that application of heat will produce an electrical current that basically translates to a voltage. Okay, and we can use that voltage in order to know what is the temperature in your environment, no, or in the object that you want to monitor. And here in this, in the right side, I am showing you an illustration of a thermocouple, no? Okay, so let me erase these drawings. The other type of device is called the thermistor, okay? And the thermistor operates in a different way because this is an example of the thermistor. Basically, the effect is as follows. You apply heat to the thermistor, and when you apply heat to this device, you will have a change in resistance. But at the end, we can measure the voltage, no? Because the change in resistance can be translated to a change in voltage. A higher resistance will be associated with a higher voltage, and a lower resistance will be associated with a lower voltage. Okay? And we have two types of thermistors. Okay? We have a negative temperature coefficient and a positive temperature coefficient. The difference between them is that the negative temperature coefficient decreases its resistance when we increase the temperature. And the positive temperature coefficient means that the resistance increases when we increase the temperature of in the environment. Okay? So this is the negative temperature resistance. The resistance decreases as we increase the temperature. And in the positive temperature thermistor, the resistance increases as we increase the temperature. Okay? So that is the difference between thermistors and thermocouples. Okay? The thermocouple changes the voltage it produces when we apply heat, and the thermistor changes its resistance when we apply heat. Also, remember that in the thermocouple, we are using a junction of two metallic objects, and that junction produces a voltage that we can use to monitor the changes in temperature. And here we are changing the resistance, okay? But also remember that at the end, we need to power the sensor. So at the end, what we are measuring is the voltage changes due to the change of resistance, okay? And well, these two, the thermocouples and thermistors are like some of the sensors that you can use. But sometimes, and this is a common sensor that is used for didactic purposes, that is called the LM35. As you can see here, the relationship between the resistance and temperature is not linear. No, it has like some exponential behavior. But in the case of temperature sensors, in particular this LM35, one of its advantages is that, well, it's a very small sensor. Also, it's very cheap. And you can power this sensor with 4 to 20 volts. And you can use a small battery and also, or maybe you can use your own computer to power this device. And also the power that this sensor demands is very low. Well, the current is 60 microamperes. So if you multiply this current by the voltage, you will have a very small power consumption. And also the advantage is that the relationship between the temperature and the voltage is linear. So for every degree of temperature, you will have an increase of 20 millivolts, okay? So there is a very good sensor because you can know the temperature, and also the relationship between voltage and temperature is linear, okay? So you don't need to perform any calibration. In fact, the sensor is already calibrated to work in this way. And the problem is that, well, if you compare this sensor to thermocouples or thermistors, well, the sensor is a little bit more costly, but, well, it's not too costly, no? No, you can buy it in any electronic store, and you can perform temperature readings very easily. And also you can integrate this sensor very easily with a prototyping board like Arduino. Well, another type of sensor that you can use to monitor certain quantities is the gas sensor. Here is an illustration of a particular gas sensor that is called the MQ5. The reason of the 5 is that it can measure, well, according to the manufacturer, 5 different types of, how can I say it? 5 different types of gases. No, we can measure liquefied petroleum gas, natural gas, hydrogen, and coal gas. Okay. And basically, the way in which this sensor works is that depending on the gas that is present in the environment, you can have a resistance change, no? Or the resistance of the sensor will change depending on the concentration of that gas. Okay. And since this sensor can, well, according to the authors, well, the datasheet can detect many types of sensors. Well, you will have different relationships between the change in resistance and the concentration of a particular gas. In fact, well, if you look into the data sheet of this sensor, you will find the following graph in which they are relating different gases with changes in resistance and different concentrations of that gas in particulars per million. Okay, this is the meaning of ppm. But there is a problem here. And the problem is that it's very difficult to calibrate this sensor in order to find this relationship, not to find it or generate these curves. Okay. And also, well, you can see or it may appear that the relationship is linear, but in fact it is not because we are using here a logarithm scale. So in fact, the relationship between the change in resistance and the concentration of the gas, okay, is not linear, it's logarithm. It's logarithmic. And also, one other problem that we find here is that, well, you will need to generate these curves or calibrate the sensor for all the following curves. For example, if you want to detect methane, liquefied petroleum gas, that is the rose line. The methane is the like the yellow with triangles line. Alcohol is this line, no, this purple line. Um, and carbon dioxide is this line, no? But they look very similar, no? The difference between them is not too much. And also you have air, no? That according to this graph, the air, well, the air changes or the concentration of air does not changes the resistance of the sensor. But the problem is that, well, you need to make a calibration and also you need to be sure that you're calibrating or you need to have a reference of the gas concentration. But you know that gases are very volatile and they like to occupy all the space that they want. Okay. So you need to perform this calibration under control conditions in order to have like a rough estimate. In fact, what I can tell you, I spent like 2 weeks trying to calibrate one of these sensors to measure alcohol, and it was a mess. No, it's quite complicated. Now, these sensors are good for only detecting, but if you want to find this equation that relates, well, that fits to this data or to this behavior, it's very complicated, you know? I don't recommend that. If you only want to detect, okay, there is some gas here, okay, that is good. No, there is no problem with that. But if you want to find this relationship between resistance and gas concentration, it's quite complicated, no? I spent like 2 weeks or 1 month with here in the laboratory, in the chemical laboratory in Sedetec trying to, or also I got to the CN, no? In the laboratories of biotechnology, and I try to calibrate this sensor and nobody can help me. No, it's a mess. No, it's very difficult. In fact, what I can tell you is that nobody knows how to do it. No, so I don't recommend this approach. But if some point of your life you want to use a sensor, a gas sensor, uh, my best advice is that you search for a sensor that is specific for the gas that you want to detect. So here in this table, I am showing you a list of sensors. For example, here is a sensor for detecting carbon monoxide. Here is the model of the sensors that you can buy, its main features and the typical applications. Okay, you don't need to memorize this table, but I am only showing you this table in order for you to have a reference to which sensor model you can use in order to detect certain gases. Okay, and in which applications you can encounter these sensors. Okay, but I don't recommend that you use this type of sensor. No, they look fine because they tell you, okay, you can detect many gases, but finding this relationship or calibrate a sensor to fit this data, it's very complicated. In fact, I don't want to say that it's impossible, But I think that you need certain equipment only to calibrate the sensor. Okay. So another sensor or that we can use is the potentiometer. The potentiometer is basically a device that also changes its resistance. The main difference is that we can change the resistance of this electronic device manually, okay? We can use like a knob that is placed here in order to change the resistance of this device, okay? In fact, if you have used stereos or you have used a guitar amplifier, the knobs that they are used to amplify the sound or to control the sound amplification are performed by using knobs. Okay? Knobs that are integrated in a potentiometer. Okay? And a potentiometer is basically a variable resistance that we can change manually. Okay, and there are different presentations. This is one of the potentiometers, and we can find potentiometers that can have different ranges of resistance. For example, this is a 20 kilo ohm potentiometer. Basically, that means that the maximum resistance that you can have with this device is 20 kilo ohms. We also have potentiometers that require a screwdriver in order to change its resistance. And these two are basically diagrams, okay, that you can encounter in, for example, in an electronic manual related to these devices. Okay, you can use the symbol, now that is like the common one, but also you can use this symbol that they call the functional diagram. No? Also here you can see that the potentiometer is also called the Weiper. Okay, well, they are basically referring to the same thing. So what are the applications? For example, you can generate voltage divider, you can generate dimmer switches or lights, you can control the brightness controls in a television, all there uses faders in audio equipment. Okay, another type of sensor is a rotatory encoder. What is the encoder? Here is like an animation that I place here. The encoder is basically a disk, okay, in which you have different holes along the perimeter of the disk. And you know the number of holes that you have placed in the disk, okay? This can be the shaft of the motor. And we can use these holes placed around the perimeter of the circle and also use a sensor, okay, in order to detect um, how many holes are in the perimeter of this disk. Okay. The this infrared sensor basically consists of two parts. We have an infrared light source. Okay, we have an infrared LED that emits an infrared light that we cannot see. Okay, because it has a frequency, a different spectrum. No, from the spectrum of light, the infrared light resides in a side of the spectrum light that we cannot see as humans. But the fact is that we can use this infrared sensor that is basically emitting a light, okay, and we can use a receptor, okay, that is called a photodetector or a photoresistor. The photoresistor is basically a device that changes its resistance in accordance to the infrared light that incides in it, okay? So we can use this disk and also, since we know how many holes we have, we can count how many times the infrared light has been interrupted. And since this device, this photodetector, can detect the infrared light, well, we can count pulses, okay? And that is why I have below this animation in which, let's say that this small circle is simulating the presence or the absence of this hole. So you can observe that when the hole, when there is no hole, we are not producing an electrical signal. But when the circle moves to the top, well, the light travels from the infrared LED to the photodetector, and we are producing a voltage, okay? And basically, this a long time is producing like a square signal, okay? And we can count the number of risings of this square signal, no, let me place it here. No, basically at the end, we are producing in this side a square signal, and we can use that square signal in order to know how many poles has been, well, to not count the number of interruptions of the light source, okay? That is basically associated with the number of holes that the disk has, okay? No? Basically, we can associate this number of pulses with the number of holes that the disk has. And based on that, we can know, for example, how many time has passed in order for this to complete a turn, okay? Or to complete the circle, no? So we can count pulses in order to know how much time it takes the shaft of the motor in order to complete a complete turn, okay? So that is basically the idea of the encoder, no? That we have a disk in which we can count the time it takes for the motor to complete a turn. And we are measuring that time based on the number of pulses that this infrared light is detecting, no? Well, is this photodetector is detecting, and also we can measure the time we need to take into account in order to complete a turn, no? Also, we have other devices that is the quadrature encoder. The quadrature encoder consists of two disks, okay? But the reason is that if you notice that there is like a misalignment, no? There is a difference between the alignment of the holes of the outer disk compared to the inner disk, okay? You can see that they are not precisely placed in the same position, no? The holes that are represented by these black squares, okay? But the reason of using this type of architecture is that we can produce two different pulses or two different square signals that they are out of phase by a certain amount of time or by certain degrees. But by using this type of architecture of this type of encoder, we can also count the speed or know the position of the shaft of the motor, but also we can know the direction, no, at which the motor is turning. For example, if the if we have well, we have two phases, no? We have phase A or two channels, sorry, channel A and channel B, that are basically associated with the disk or the pulses associated with the outer and with the inner circle. So based on that, we can have two channels or two signals. And for example, if phase A and phase B is leaving phase B, we can say that the motor is turning in a clockwise direction. But if phase B is leaving phase A, we can say that the motor is turning in a counterclock direction, okay? So that is the purpose of using two disks with two different holes that are misaligned between each other, because based on these misalignments and also the square signals associated with each of the disks, we can know if the motor is turning in one direction or the other one, okay? So this is basically an overview of the sensors, no? That we can use to monitor any electric motor, okay? Or to control the electric motors. So let me stop the video for now, and then I will make a second part for this video related to how we can acquire signals. Okay, so see you later.